Okay, as promised, I'm going to go through the example of carbon monoxide again, so that you are 100% clear on how we do things. Okay, so essentially, what we've got is we have some information that we need to write down. Just let me get a pen handy. Right. So for carbon monoxide, we need to get some information. Okay, so we know that we have to use the table, and I'm going to give you the data again. So it's 2s orbital is for carbon, has a value of minus 19.43 electron volts, and for oxygen is minus 32.38 electron volts. Okay, and then for the 2s, the 2p, we have carbon as minus 10.66 electron volts, and the oxygen is minus 15.85 electron volts. Okay, so now what do we need to do? We need to look at the interaction. So we're going to say, okay, carbon 2s orbital, can it overlap with the oxygen 2s orbital? Okay, we can have a look at that and we can establish if there's an energy difference. Okay, so we have the energy difference. Let's calculate that. And we know that we can say it is oxygen, where are we now? 2s. So that's minus 32.38, minus 32.38, minus 19.43. That gives us negative 12.95 electron volts. Okay, so we can definitely have an interaction there. It's on the border of it being an interaction, but it does exist. Okay, and we can then look now at the 2p's, 2p and oxygen 2p. We have an energy difference of, where is the 2p's now? So that's minus 15.85 minus 10.66, and that gives us minus 5.19 electron volts. So we'll definitely have an interaction there. And then lastly, can the 2s and 2p mix? Okay, so that's what we need to look at. Carbon 2s and oxygen 2p. Can we get a mixing? And we can definitely have a look at that and say, right, oxygen 2p is minus 15.85 minus minus 19.43, and that will give us 3.85 electron volts. And of course, that is quite a small value, which does imply that we're going to get S and P mixing. Okay, so I'm just going to put it like that. Okay, so that's the energy calculations. So what we need to do now is we need to construct the diagram. All right, so let me just move this up a little bit so we've got some space. Okay, and now we want to draw the energy, first of all, that's important. Okay, and I'm going to put the carbon this side and the oxygen on this side. Okay, so we're going to work with carbon first. I'm going to put the 2s over here, and I'm going to put the 2p's up here. Okay, so that's the 2p. Now remember that the oxygen is lower in energy. Okay, so we need to put this one down here somewhere. Okay, so we've got 2s, and then the 2 p's are a little bit lower down. So that's the 2p for the oxygen. You can see they're not on the same level. If you're looking at my mouse that's moving, they're on a different level. Okay, so now let's make the carbon monoxide molecular orbitals in the middle. Okay, so remember that 2s and 2s can interact with one another, and we're going to get the sigma molecular orbital here. So it's as a result of the s interaction. Remember, it's a bonding orbital. Because it's s orbitals, it will be Gerada, okay? And then we are going to have an antibonding orbital, which is roughly slightly less than the 2s of the carbon on its own. So this is going to be the sigma star. It will be from the s interactions, and remember that it's ungerade. Okay, now, what about the electrons? Let's just put the electrons in. So remember that we've got the 2s, and then we've got 2 electrons there. And with oxygen, we've got the 2s electrons here, and we've got 1, 2, 3, 4. Right. Let's pair these up. So we've got 2 electrons from the 2s and 2 electrons from the 2s here. Let's put them together. We have 1 going into the bonding, another one from oxygen going into the bonding. Okay, the next one from carbon, and the next one from the oxygen. Okay, so that's roughly going to give us the interaction for the 2s interaction of both orbitals. Okay, right. So that takes care of how we fill the electrons for the 2s interaction. Now, let's do the 2p interaction. Remember, there's orbital mixing, so we have to put these orbitals in the opposite way around. So we're going to have the pi orbitals lower than the 2p orbital of oxygen. So we're going to put the 2 orbitals like that. Those are going to be the pi interactions from the p, and remember that they're bonding interactions, so they're going to be ungerade. Okay, then we're going to get the sigma overlap. Okay, it's a p overlap, and that is gerade because it's bonding. Okay, and then of course the normal way that we represent the antibonding orbitals, we've got the pi star, and that is from the p or interaction, and it's gerade, and then the last one is the sigma star from a p overlap, and it's ungerade. Okay, so now we have a total of 1, 2, 3, 4, 5, 6 electrons that need to go in here. Okay, so let's just connect the orbitals. So we've got a connection here to say that this is a p interaction, and remember we have s and p mixing, and that's where we show this with the swapped pi and sigma orbitals. So there is the completed interaction like that. Okay, now we can fill the electrons. Okay, so we take 1 electron from carbon, and we first fill the pi orbitals, 1 electron there, and another one can go in there. Okay, and we take another one of the electrons that can come from oxygen, 1 there and 1 there. So we are now almost completely left with only electrons from the oxygen to complete, which would probably go into the s and the p orbital to indicate the mixing. Okay, so we put them like that. So we've got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, and that completes the molecular orbital diagram for carbon monoxide. Okay, now I did say to you that we would be able to calculate the bond order. Okay, so if I moved up the whiteboard just a little bit so that I can move it slightly over so we can do the calculation on the right-hand side here. Remember, that bond order is equal to 1/2 of the bonding electrons minus the anti-bonding electrons. Okay. This down the bottom here effectively is going to give us a zero calculation. So let's just work with the 2p section, the 2p atomics and the pi and the sigma p orbitals. So if we have a look here, we have it's 1/2. How many bonding electrons do we have? Well, we have 2, 4, 6. How many anti-bonding electrons do we have? We have none. So that means that the bond order is 3. This is consistent then with the Lewis diagram for carbon monoxide, where we put carbon and 3 bonds to an oxygen. Okay, so that's the how we would solve the solution to drawing the molecular orbital diagram for carbon monoxide and to calculate its bond order. Okay, so let's now go to the HF example so that you can see how the electrons are filled there. Okay, so I was going to move this up. Hopefully I have enough space on the board. I think I should have. If not, I think probably the easiest thing would be for me to just clear the canvas and we could start over. Let's do that. Okay, let's just bring this thing all the way down. Okay, that's as far as it can go. Okay, so now if we do the, sorry, it helps if we have a pen, MO diagram for HF. Okay, so how did we do that? Well, first of all, remember we need to look at the orbital energy. So we need to go to table 5.2 and we need to have a look. So the hydrogen 1s has an orbital value of minus 13.61 electron volts, and the fluorine 2s has a value of minus 40.17 electron volts. There are no p orbitals in hydrogen. What we need to look at for the fluorine is we need to look at the 2p orbitals. They have a value of minus 18.7 electron volts. Okay, so now what can we interact? Can there be any interaction? Well, what we need to do is look, can the 1s overlap with 2s? Well, we need to do the calculation, so let's try that and see. So we have hydrogen 1s plus the fluorine 2s, okay, and we need to work at the energy difference. So we say minus 40.17 minus 13.61, and that gives us an answer of 26.57 electron volts. So that would mean no interaction. We can't get a bonding interaction because the energy difference is too big. Okay, so then we need to look at the hydrogen 1s and the fluorine 2p. That would make a whole lot more sense. So we've got minus 18.7 minus 13.61, and that gives us a value of 5.1 electron volts. So we can definitely have interaction there. All right, so now let's draw the diagram. Okay, let me just push this up a little bit. So we know how to construct this. Let me draw the energy here for you. Remember, always draw the energy, indicate the energy. All right, and we start with hydrogen on the left, and we'll have fluorine on the right, and we'll have HF in the middle. Okay. Now, the 1s is vastly different in hydrogen. It sits way up here, okay? If I draw the 2s for the fluorine, I'm going to draw the 2s down here, okay? Because the value is minus 40, and then the value for hydrogen is minus 13. So that means that the 1s is somewhere up here. It's ridiculous, the energy gap between the two. Okay, so we've got 1 electron in there, and we know that we have 2 electrons in the 2s orbital. All right, there is no interaction. As we see here, there is no interaction. So essentially, we can draw the sigma non-bonding orbital, okay? It's the same orbital. I'm going to draw it in green because it's a molecular orbital, but it's a non-bonding orbital, and it's got those 2 electrons in that contribute from the 2s of the fluorine. Okay, now we can deal with the, let's make this nice and simple, so we connect the dots like that. Okay, now let's have a look here. So we do have, for the p orbitals, let me just draw them. Sorry, I've forgotten to draw them. So we've got p orbitals here for the fluorine, and we've got 1, 2, 3, 4, 5. That's 2, 4, 6, 7. Okay, valence electrons for the fluorine. Okay, so we have an interaction between the 1s and the 2p. You can see that over here it says it's 5.1 electron volts is the difference. Okay, so we can draw an interaction that is somewhere down here. That is a sigma. It's a bonding interaction. So it's a sigma as a result of S and P, and it's obviously Gerarda because it's bonding. Okay, and then the sigma star is somewhere up here. Okay, sigma star, and that'll be ungerada. Okay, so that'll be a contribution from the 1s orbital of the hydrogen and the 2p orbitals of the fluorine. Okay, now we only have 1 electron from the hydrogen that can go here, and 1 free electron from the fluorine that can go here. Okay, so they sit in the bonding orbital. The remaining 2p orbitals, there's no interaction. Remember what I told you guys, that if an S and a P are not of the same symmetry, so we have this constructive interference. So here's, let me just draw it in a different color. Let's pick a color now. All right, we'll go with this. So we have an S orbital, okay, and then we have a p orbital, which I'm going to draw like this. That this here, okay, let me just, this interaction here is constructive interference, this interaction here is destructive interference, and therefore it's a non-bonding interaction because the interference cancels out. So that's what happens here. So essentially what happens is we're on the same energy level, we draw the 2 orbitals, they're on the same energy level as the atomic orbitals. They are non-bonding interactions, so they are pi non-bonding interactions, and the electrons that contribute there come from the 2p. And that's essentially how we will construct the diagram for HF. Now, I did say that I would help you with the bond order calculation. And remember that, let me just move the canvas over a little bit so that you have, we'll try and keep it so that, now, remember that bond order is 1/2 of bonding electrons minus anti-bonding electrons. Okay, where are the bonding electrons? Well, there's only one set of bonding electrons. Okay, remember that these guys here are non-bonding and these guys here are non-bonding. They don't contribute to the bonding. In order for us to calculate the bond order, we need to either have bonding electrons or antibonding electrons. We have no antibonding electrons, and we have 2 electrons over here that come from a formation of a bonding orbital. So it's 1/2 of 2 minus 0, which equals 1. This is then consistent with the Lewis diagram for HF, which shows 1 bond between the 2 atoms.